So we should start the lecture in the morning. And then the first lecture will be given by Professor Harada. And here I make a brief introduction to his career. He received his PhD degree in 1993 from Nagoya University. Actually, he received all his academic degrees from Nagoya University. So I'm not sure whether he was born in Nagoya. And then he went to Kyoto University as a postdoc with the JSPS fellowship. He spent 2 years in Kyoto. Then he went to the United States, spent 3 years there. He was a postdoc of the Syracuse University and also the University of North Carolina. Then he returned to Nagoya in 1998 as an assistant professor. And he's now a full professor there. And Professor Harada has a strong background of astrophysics. And he studied the ATS-QCD in the past few years. So I think it's quite appropriate for him to give a lecture on this age of March based on holographic QCD models. Okay, let's welcome Professor Harada.
Thank you very much for your introduction. First of all, I'd like to thank you, organizers, for inviting me to here. Actually, this is the first time for me to come to Taiwan. Today, it is a great pleasure to give this talk on the hadron technology based on our QCD models. Okay, then let me start with, from the introduction. Then brief introduction. Actually, this is a very brief introduction, starting from the showing an example phase diagram of system in quantum-based matter. This horizontal axis is the density or chemical potential, while the vertical axis, this axis shows the temperature. And our world is this area where the chiral symmetry is spontaneously broken and the quarks are confined inside the hadron. When the temperature is increased in this way, the chiral symmetry is expected to be restored, and the quarks are completely cold. So this phase is called the cold room plasma phase, shown by this pink color. On the other hand, when the density is high, also the chiral, on the other hand, when the density is high but the temperature is low, the color superconducting phase is expected, where two quarks makes Cooper. This high temperature region is expected to be realized in early universe, as some of you may know. And, so that studying this region will give us a clue to understand the early universe. And there are several experiments to study this region ongoing, such as the still big experiment and the heavy ion experiment ongoing. On the other hand, the low temperature region and low temperature and high density region is important for understanding the neutrons. And in these days, I'm interested in this high temperature, high density region. High density region, and as you know, it is very difficult to study this phase structure from QCD directly, since the QCD is just a coupling gauge theory. One of the powerful tools to study QCD is the lattice QCD. However, the lattice QCD is not applicable in high density system due to the sign problem. So, using effective models may give us some clue to understand what's going on in the high density. Then, among many effective models of QCD, I pick up an holographic QCD models in this talk. Holographic QCD models are based on the so-called gauge gravity correspondence, which says that the strong coupling gauge theory in 4 dimensions corresponds to or equivalent to the gravity in 10 dimensions. And then the solving classical equation in this slide will provide the information of the physical quantity with full quantum effect in this 4 dimensions. And please note that this correspondence is formulated in the large NC limit. In the large NC limit, QCD becomes a weakly interacting theory of mesons, and the values are given as solitons existing in the mesonic theory. And another feature of holographic models is that the models are constructed in the large half coupling region. Okay, there are many analyses based on the holographic QCD models, but most of them study low energy hadron phenomenology directly. Okay? This is a most analysis people study the low energy hadron phenomenology directly from this holographic QCD models. However, there is another way of studying in which the holographic QCD models are reduced to 4-dimensional hadronic effective model, such as the hydrogen model, which I will explain later. And actually, using hadron effective model at intermediate step may give an interpretation of the result from holographic QCD models in terms of light mesons such as Robinson pi. So it is useful for understanding if we use the 4-dimensional hadronic effective models at the intermediate step. Then also that this may give a clue to understand what we can learn from the holographic QCD and from the other QCD. Then in my lecture, I would like to introduce some of my recent works where I developed this way of analysis. And I also will give us some my analysis on this direct study. Okay, this is an outline of my talk in these 3 days. In the first chapter, I will give you some brief introduction of hardware model, which is an holographic QCD model. Which one holographic QCD model? And then in the chapter 2, I will introduce the hidden local symmetry model, which is an four-dimensional effective model. And in the section 3, I will relate one product model, which is called Sakai mode model, to the hidden local symmetry. Then next, these 3 chapters are for my study on the direct analysis of the direct analysis of the low energy Hadamard technology from the QCD model. And then probably, I think that these are enough for 3 days, but if I have time, I may introduce some my recent work of this, where that I use this model of hidden local symmetry, where the parameters are determined from the homological QCD to study the some properties that finite density. Okay, let me introduce so-called Hadamard model proposed by all these people. And some points in this section is also based on this work of our cooperation. But if you have any question, please ask any point. Okay, let me start with this slide, which is quite similar to the one which I showed in the introduction just a few minutes ago. This slide shows that gauge gravity correspondence says that the strong coupling gauge theory in the 4 dimension is equivalent to the gravity in 10 dimension. Then solving classical equation of motion in this side will provide physical quantities with full quantum effect in the 4 dimension. But this correspondence is formulated in the large edge limit of QCD and also large coupling limit. Okay, then let me show this correspondence in using some equation. Please consider that this Z is a full generating function obtained in a 4-dimensional gauge set. Here the Q, Q5, blue. And then this is a full generating function obtained in QCD. Here that this phi 0 is an external source field. And the operator, this O is an operator corresponding to this source. And standard quantum field theory tells us that if you differentiate this generating function in terms of phi 0, external source twice, for example, in that case, you will obtain the correlator. And this is a correlator of this operator. And this is a standard procedure of in quantum field theory. On the other hand, okay, then okay, then this S phi is a classical effective action in the 5-dimensional theory, which is obtained in the holographic QCD model. Here, this phi is a 5-dimensional field. Okay, then this at the and Z is a 5-dimensional coordinate. Okay, then when this is a schematic picture of 5-dimensional coordinate, and then this 5-dimensional coordinate has an edge. This is edge where the 4-dimensional gauge theory lives. For example, that in the holographic QCD, and this is this our world is at this point where Z equals 0. Okay, Z or epsilon. Okay, epsilon is a very tiny quantity. And now the gauge gravity correspondence implies that when the value of phi at UV this is called UV plane. The UV limit is identified with the source term. Then this action, effective action at the classical level, becomes equivalent to the full effective action, full generative function obtained in the four-dimensional gauge theory. Please note that this five-dimensional five-dimensional action is obtained at classical level. So we may be able to calculate it once we have some model. Then this, on the other hand, it is very complicated or difficult to calculate this generative function with including all full quantum method. Okay, then next, let me show how the effective confinement of QCD is included in the picture. In the duality, which I explained in the previous slide, the UV boundary is regarded as our. This is a five-dimensional, and then at the edge, our bar is at edge, which is called UV boundary. On the other hand, the effect of the confinement is included by putting an IR cap in this fifth direction. Namely, a four-dimensional brane is put at this. This brane, called IR brane, is put at some point. And this brane is called, and I use ZL for this coordinate at which the IR brane is put. Now, please note that the dimensional field, so five-dimensional field phi lives only between this UV brane and IR brane. Then this doesn't exist at this side. Then in other words, this is a horizon. Then you cannot go beyond this IR brane. This phi can live only between UV brane, which is our bar, and IR brane. In that sense, that we cannot. This is IR brane, that this is low energy region. Right? Then in the low energy region, because of the confinement, we cannot enter this energy region. This is called effective confinement. Now, let me show the action of this model. As usual, the action is obtained by integrating the Lagrangian test. But here, please note that this Lagrangian, this action, so the integration is over 5 dimensions. And also that, please note that the range of the integration over fifth dimension, dimensional coordinate, is from UV boundary, located at z equals epsilon, to the IR boundary, which is located at z equals Zm. Now, since the hardware holomorphic model is based on the ADS background, the metric of the space-time is not flat, as you can see from this form. Please note that the existence of this A factor, which is given by 1 over z. And this square root g is given by 1 over z to the pi. Well, in my talk, that I use this metric, that for the time component corresponds to 0, this 1, and the space component corresponds to -1 in a Minkowski metric. And this is a metric, and also in this Lagrangian, this FL and FR are the field strength of the gauge field in the 5 dimension. This FL and FR are the field strength of this gauge field L or R, L and R. And also this N runs from 0, 1, 2, 3, and then 5, or Z. Sometimes I use Z. This V is a vector field, which is the sum of left and right gauge field, and A is the axial gauge field. And this X is a scalar field, and the covariant derivative of this X is given by this one. And this is our model. This is a Lagrangian in this model. And then let me show the ADS-CFT so-called ADS-CFT correspondence between 5 major fields included in the model and 4 major operator. And this AL, okay. In the previous slide, I used the LM. I'm sorry that I picked up I cut this from the different paper so that the notation is not consistent. But this AL is a left hand gauge field and corresponds to this left hand current, Q bar L, QL. Q bar L, gamma mu, QL. This TA is the generator for that flavor group. Here, this P is a spin carried by the operator, and this delta shows the dimension of the operator. Then this 5-dimensional mass square is calculated by this formula. This is a dictionary. And as you can see, this left-handed current operator carries spin 1 and dimension 3. Then using this formula, you can calculate the 5-dimensional mass is 0. That's why there is no mass term in this branch, only the kinetic term of the gauge field. On the other hand, this X field multiplied by factor 2 over Z corresponds to this scalar type density operator. Since this operator does not carry any spin, P is 0, and but the dimension is 3 again. Then the mass square becomes minus 3. And then here that the mass square is minus 3. Then this is a Lagrangian. And then let me discuss the first 5-dimensional chiral symmetry. I introduced gauge symmetry at 5 dimension, but actually that is related to the chiral symmetry. That is regarded as a chiral symmetry in the 5 dimension. And then in this Lagrangian, the chiral symmetry exists, or 5-dimensional chiral symmetry exists, but that is a gauge symmetry. The symmetry, okay, for definiteness of this talk, I restrict myself to the 2 flavor cases. Then the chiral symmetry in this Lagrangian is U2 cross U2. The transformation properties under the chiral symmetry is of the fields are given by this form, given by these forms. X transforms Y fundamentally under the chiral symmetry, while M is a gauge field corresponding to the U2 left. And also I omitted, but R is a field, a gauge field for U2 right. And then, of course, when the X field has its pair, this chiral symmetry is spontaneously broken. But for example, if this pair is diagonal, then U2 vector symmetry remains, and this chiral symmetry is broken down to U2 vector symmetry. Next, let me show how this 5-dimensional gauge symmetry is related to the 4-dimensional global chiral symmetry. In our world, as I said before, that our world is located at the edge of the 5-dimensional space. So we want to know the relation between 5-dimensional gauge symmetry and the 4-dimensional global chiral symmetry. Then for this purpose, let me make the UV boundary condition like this, where there is no source term at the UV boundary. As I said, that if you want to relate, if you want to get some generating function, you want to put some source term. But okay, here, let me cut this source term, and means that implying that this 5-dimensional field at the UV boundary vanishes. Then you can easily see that this boundary condition is invariant under this gauge transformation when these conditions are satisfied. If you this m runs from 0 to 5, then all this means that at the edge or at the UV boundary, this gauge transformation does not depend on x and z. Then this implies that there is a global symmetry at the UV boundary, which is identified with the chiral symmetry in the 4-dimensional QCD. You can understand that this is a gauge symmetry which originally existed. But if you make this boundary condition, the entire gauge, some part of the gauge symmetry is broken, but still there is a global symmetry remains at the UV boundary, which is identified with the chiral symmetry, global chiral symmetry in the 4-dimensional QCD. Okay, let me show the UV and IR boundary conditions of the relevant field. And, this is phi implying here this phi implies either of x or vector field, pH field, or axial vector pH field. As I have explained before, the ADS CFT correspondence implies that the 5-dimensional field at the UV boundary becomes a source term in the 4-dimensional gauge theory. Then, on the other hand, the IR boundary conditions are determined in this way. Here, let me start from the Lagrangian and the 5-dimensional action. And this is very schematic, by the way. And you can obtain this form by making integration by part. And when the solution, then this part becomes the equation motion. And if you substitute the solution of the equation motion, this part vanishes, while the boundary terms remain. And the UV boundary action, UV boundary part is needed for the ADS CFT correspondence, because at the UV boundary you have a source, and if you differentiate this action in terms of this source, you obtain some the expectation value of the operator, or current correlator, and so on and so on. But you don't need the IR boundary or IR boundary action. Then vanishing IR boundary action can be realized when you put this IR boundary. And usually in this Broad QCD model, the field, 5-dimensional field at the IR boundary satisfies this condition. Okay,